Chapter 7, Probability and Samples, the Distribution of Sample Means, Part 2. In the previous lecture, we used example 7.1 to demonstrate the construction of a distribution of sample means for a very simple population. In fact, the population only consisted of 4 scores. The distribution of sample means was constructed using 16 samples with each sample containing 2 scores. The reality is that populations are quite large, and it is unrealistic to think that we would be able to reconstruct or construct a distribution of sample means using all possible samples. With larger populations and larger samples, the number of possible samples increases significantly, and it is essentially impossible to actually obtain every possible sample. Fortunately, it is possible to determine exactly what that distribution of sample means looks like without taking hundreds or thousands of samples from the population. Specifically, a mathematical proposition known as the central limit theorem provides a precise description of the distribution that would be obtained if you selected every possible sample, calculated every sample mean, and constructed the distribution of sample means. The central limit theorem is a cornerstone for much of inferential statistics, and it relates to the following points. So the central limit theorem applies to any population with a mean of mu and a standard deviation. The distribution of sample means approaches a normal distribution as n approaches infinity. Essentially, you can understand the central limit theorem as follows. As sample size, and I'll write it down here, as sample size increases, the distribution of sample means becomes more normal. And what I mean by more normal, or what we mean by more normal, is this ideal bell shape. We can also have distributions that are flatter, that we'll talk more about in just a sec, or more peaked. But this is the ideal normal distribution. So what we're saying is that if you collect samples, the larger the sample size is, the more normal the distribution of sample means will become. So again, reflect back on the example we walked through in the previous video where we took all possible samples, sample size was equal to 2 scores, and we constructed a perfectly normal distribution. And that was as a result of having a normal population to begin with. But here we're stating that as n increases, that distribution will become more normal, more peaked, meaning we'll have higher frequency of sample means in the center of the distribution. So distribution of sample means for samples of any particular size will have a mean of mu sub m. And we learned in the last video that mu sub m is in reference to the mean of sample means and is always equal to mu, the population mean. So again, we walked through that example and we constructed all possible samples from a population size of 4 scores, and that yielded 16 different samples, and we calculated the mean for every sample for all 16 samples. Then we calculated the mean of sample means, the average of all those sample means, and we learned that that was equivalent to the population mean. Finally, distribution of sample means for samples of a particular size will have a standard deviation equal to the standard deviation of the population over the square root of n. And again, that is how we calculate this new concept that we refer to as the standard error and it's equal to the standard deviation of the population over the square root of n. In the last video, I presented that standard error is similar to standard deviation. Standard deviation is the average difference between scores in a distribution and the mean of the distribution. Standard error similarly represents the average difference, but instead of between scores and the mean, it's the average difference between sample means and the population mean, which again, the population mean is equal to the mean of means, and it's denoted by this variable here, mu sub m. Note that the central limit theorem describes a distribution of sample means by identifying the three basic characteristics that describe any distribution. These three characteristics include the shape, the central tendency, again the central tendency being the mean, and variability. In this case, variability is represented by the standard error of the mean. And we're going to consider all three of these in the subsequent slides. So the first characteristic we'll consider is the shape. The shape of the distribution of sample means. The distribution of sample means is almost perfectly normal in either of two conditions. First, if the original population from which the samples are selected is normal, then the distribution of sample means will also be normal. So reflect back on the example in the previous video. And it was example 7.1 in our text, where we took original population distribution of 4 scores, calculated the mean of all possible samples, and we ended up with 16 different samples and 16 different sample means. We took those sample means and then constructed a distribution of sample means and noted that it was a perfectly symmetrical distribution, a normal distribution. And that resulted from the fact that the original population of scores was normal to begin with. If the original population distribution is not normal, if it's either positively skewed or negatively skewed, then we can still apply the central limit theorem when constructing the distribution of sample means if the sample size is at least 30. So n must be greater than 30 to result in a distribution of sample means that is normal. So again, if the original population distribution is skewed and we want to construct a distribution of sample means that is normal, we must select sample sizes that are at least 30 or greater. And by doing so, mathematicians have confirmed that 30 seems to be the magic number, that as long as the sample size is 30 or more, the distribution of sample means will be normal. So again, as long as you meet one of these two conditions, note the word or, then we can rely on the central limit theorem and use probability to determine the likelihood of a particular sample mean. The next characteristic we'll consider is the central tendency, specifically the mean. And we entitled this the expected value of m. The mean of the distribution of sample means is equal to mu sub m, right? And I've indicated that that's the equivalent of the mean of means. And mu sub m has a value equal to the mean of the population of scores. So for our purposes and for the examples that you'll have to solve for your homework and the quiz and the exam, mu will be given. So mu is a given value. And I point that out because sometimes you'll be asked to identify the expected value of m, and mu will have been given, and students sometimes freeze and aren't really sure what to do. All you need to do is restate mu. So again, if you're asked to identify the expected value of m and mu has been given, please recognize that the mean of sample means will always equal mu. The mean of distribution of sample means is referred to as the expected value of m. So again, this character here is what we mean by the expected value of m. And the expected value of m can also be expressed as the mean of sample means. In the previous example, example 7.1, we demonstrated how taking all possible sample means and computing the mean of those sample means did yield and equal the population mean. M is an unbiased statistic, and we'll recall what unbiased means. Again, the unbiased statistic is identical to the population parameter. And the reason M is an unbiased statistic is because we are taking these values from the population. In other words, when we're calculating the sample mean of all possible samples, if we have access to all possible samples, as we did in the case of example 7.1, we had 16 samples, all of those sample means consisted of all the values that we saw in the population. So it would make sense that the mean of sample means would yield the population mean. Therefore, we consider that an unbiased statistic because it's equivalent or equal to the population parameter, in this case, the mu. So again, M is an unbiased statistic because the mean of sample means, or the expected value of the distribution of sample means, is the value of the population mean. When the sample statistic is unequal to the population parameter, as in the case of sample variance, then we consider that to be a biased statistic. But here it is unbiased because the sample statistic is identical to the population parameter. The third characteristic is the standard error of mean, or M, and is representative of the variability. So we learned about different measures of variability, which included variance. Well, we began with the range, variance, and standard deviation, and we focused on the most important measure of variability in Chapter 4, which was standard deviation. Again, by definition, standard deviation is the average difference between scores in a distribution and the mean of the distribution. And standard error of M, or standard error of the mean, is similar in concept. It's giving us a standard or average difference, but instead of that difference being related to X values, we're talking about the difference between M values and the mu of a distribution. So variability of a distribution of scores is measured by standard deviation. Again, the average difference between scores and the mean of the distribution. The variability of distribution of sample means, which is what we're talking about in this chapter, is measured by the standard deviation of the sample means and is referred to as the standard error of M, and expressed using this variable, which is lowercase Greek sigma sub m. So again, conceptually, it's the same idea as standard deviation, but instead of talking about X values, we're talking about sample mean values. And just a side note, in journal articles or other textbooks, you may see the standard error of M might be identified as SE or SEM. So for those of you who will go on to take the lab component of this course, you will notice that you'll be utilizing a statistical program called SPSS, and with that program you'll see these types of acronyms that represent these different statistics. So it's something to be aware of when you take the lab component of this course. So again, just to review, the standard error of M is the standard deviation of distribution of sample means. So again, if we refer to the standard deviation, which is representative variability, then we just include this other terminology, which is standard error of M. And again, variability denotes how consistent scores are. So we can have a distribution that is really consistent, right? Most of the scores are centered around the mean, or we have a distribution where the variability is really inconsistent, or we have scores that are very inconsistent. There's a greater range greater variation in the sample means, and it would be visually interpreted in this way in the second graph here. So in the first graph, we can pretend like we have different samples plotted. And we may have this sample mean. And again, we understand that these values, sample mean values, differ from the center value that represents the population mu. Let me just put some numbers to this. Let's say the population average was 50, and this sample average was 51. This one was 52, and this one was 53. This was 49, and this was 48. And let's say we derive those sample means by taking samples of 100 individuals. So 100 X values were computed to produce these sample means. And let's say we have another distribution that also has a population mean equal to 50, and we take a sample, and this one's equal to 55, and another sample of 60, and another sample over here of 45, another one here of 65, another one here of 45, and again we took samples that were equal to 100 X values or scores, and they produced these sample means. Again, the standard error, similar to standard deviation, tells us how consistent the scores are in distribution. In this case, how consistent the sample means are in relation to the population mean. So again, we see that 50 differs from 51 a certain amount, 50 differs from 49, 50 differs from 48, 50 differs from 52, and also 53. Similarly, these all differ by a certain amount. The standard error is going to give us the average difference. And as we can see, the flatness of this second distribution shows that the scores are more spread out, and therefore we see less consistency, whereas in the first graph we see that there's a higher concentration of scores here in the center. Here they're more spread out, and so the range of those scores is much greater. And again, the value of the standard error will indicate to us essentially the expected or average amount between the sample mean and the population mean, any sample that we select from the population and the population mean. So again, as I stated before, it's similar to standard deviation, but now we're just expressing an expected difference between the sample mean and the population mean. Along the lines of discussing what standard error represents, we need to understand the law of large numbers, So the magnitude of the standard error, the magnitude of the expected difference between the sample mean and the population mean, is related to how large of a sample we're working with. So technically, we should understand that the larger the sample size, so the larger n is, the more probable it is that the sample mean will be close to the population mean. So we're saying, again, we have a distribution. It's normal because, let's just say, our n is greater than 30, and or the original population was normally distributed. And as n increases, the probability of a sample mean being close to mu increases. And why would that be the case? Well, if we're increasing the number of X values, again, m is equal to the sum of X over n. So if we increase the number of X values that we're using to make up or create a sample, then we're taking more values from the population. The sample becomes much more representative because we're including more possibilities that exist in the population, and therefore the sample mean that's produced or calculated will be closer to the mu of the population. It'll center closer to the population average than if n is small. When n is small, then the probability of obtaining a sample mean that's close to the mu is lower, simply because, let's take, for example, if we just took a sample of 2 scores, it is possible that the 2 scores may be 2 x values on the extreme side. And so if we calculate a sample mean of just 2 scores and by chance they happen to be extreme scores, the sample mean will be much further from the population mean. So again, the law of large numbers states that the larger the sample size, the more probable it is the sample mean will be close to the population mean. And again, the explanation for that is because as we increase the number of x values in our sample, the more representative the sample becomes. Next, we should recognize this idea or understand the idea of variance as it applies to the distribution of sample means. So population variance. So if the original population variance is large or small, that will have an effect or impact on the distribution of sample means that is created. So the smaller the variance in the population, the more probable it is that the sample mean will be close to the population mean. So similar to what we said about the size of the sample, here we're saying as variability of a population decreases, the probability of obtaining a sample mean close to mu increases. So again, if we say the variance is small in a distribution, let me just erase this here. If we say the variance of a distribution or population distribution is small, again, variance leads us to standard deviation, so we're saying low variability or low variance. That also means low standard deviation. And we're saying that the distribution is more peaked, right? We have a higher concentration of values centered around the mu. And therefore, if this is the case, we're saying that the majority of x values in the population are similar to mu. So if we take a sample from that population, then the likelihood of the sample mean being similar to mu is also very high because the majority of x values are centered around the mu. So if we take a sample, most of the scores are going to be around mu, meaning they're very similar to mu. And if we take a subset of that population and then take a sample and then do that consistently over and over again, the distribution of sample means will also be very peaked and show very low variability. Conversely, the opposite would be true, that if we have a distribution that's very spread out, meaning that there's great variability, variance is high, standard deviation is high, then the likelihood that the sample mean will be similar to mu is less because, again, if we're taking x values from this distribution to create a sample, we have great variability in these x values. They're very spread out. And therefore, the variation of the sample mean is going to be different than the population mean. In other words, it won't be centered around that mu because the x values that we're selecting may all come from these extremes, right, or a mixture of all of them. But we noticed that initially these scores were very different from the center to begin with. And therefore, if we take a subset of those, the likelihood of those values being dissimilar to the mu is high. Therefore, we would see that reflected in the distribution of sample means. What this all means, or if I can simplify it or summarize it, things to remember are that larger sample sizes are good and low variability in a population is good as well. But we don't have any control over variability of the population. That is what it is. That's a parameter, a fact that we cannot change. But the size of the sample is something that the researcher has control over. So we'll see how increasing sample mathematically will produce lower variability in the distribution of sample means. So we'll look at the equation for computing standard error in just a moment. But again, we want large samples because they're representative, and we hope that the original variability of the population is low because differences that are reflected in comparing samples after treatment are more evident or visible. Figure 7.3 illustrates the important relationship between standard error and the size of a sample. So we just discussed the law of large numbers, which indicated that larger samples are going to produce, first of all, more representative sample means centered closer to the population mean, and as a result will help in constructing a distribution of sample means with lower variability. And lower variability is important because when we have a distribution with less variance or variability, the differences that we are hoping to detect due to treatment are more evident. In other words, when a distribution is very spread out, it's hard to pinpoint why we would generate a sample mean that's unlike the population mean. If the original distribution is very different or diverse to begin with, then it becomes more difficult to contribute any extreme sample means to treatment opposed to simply the fact that the original distribution was wide in range, illustrated great standard deviation or variance or variability. So let's review the equation for standard error that was briefly presented before. So standard error of the mean is equal to the population standard deviation over the square root of n. So we see now that standard error is a representation of variability of the distribution of sample means, and it tells us on average how much we would expect a sample mean to be from the population mean. And the further it is on average, the greater the variability. The closer it is to the population mean, less variability. And again, we would anticipate the majority of the scores are going to be centered around the center of the distribution based on our understanding of the shape of a normal distribution. Again, we have the majority of values here, whether they're scores or sample means. And if we want to detect differences, obviously that means a sample mean that's going to be over here somewhere or over here, because that illustrates differences. Now, this relationship between standard error and the size can be shown mathematically. And briefly, we should understand that as n increases, the standard error of the mean decreases. And again, we want lower variability in our distribution of sample means. We have no control over the variability of the original population, but when we take samples from that population, if the sample size is larger, the variability of the distribution of sample means will be smaller. And again, the purpose and function of having a distribution with low variability is to have the capability of detecting differences more easily. So let's look at this graph. This graph illustrates this quite nicely. Here on the x-axis we have the sample size, and we're working with the distribution that has a standard deviation equal to 10. And we're going to calculate the standard error given a change in sample size. So in the first example, we'll work with this value here. When n is equal to 1, the standard error of the mean would equal 10 over the square root of 1. And so our standard error would equal 10. So when the sample size is equal to 1, the standard error of the mean will equal the population standard deviation. This is important, so I will repeat that. When n is equal to 1, the standard error of the mean will always equal the population standard deviation. And the reason is because if we're taking a sample of 1 and generating all possible samples, we're essentially recreating the original distribution of x values. So that should make sense to you, that again, the standard error of the mean will equal the population standard deviation when n is equal to 1. Now let's increase it to this next value of 4. So when n is equal to 4, our standard error of the mean is equal to 10 divided by the square root of 4. So we have 10 over 2, and we get 5. So what happened to the standard error? Again, as n increased from 1 to 4, our standard, and I should maybe write the arrow in the other way, right? So we have an increase from here to here, from n equals 1 to n is equal to 4. So the sample size increased and our standard error decreased, which is good, right? Again, the law of large numbers says that the larger the sample is, the more representative it will be of the population mean, and therefore be concentrated and centered around the population mean. So we have lower variability. Now let's look at the next one. If n is equal to 9, our standard error is equal to 10 divided by the square root of 9, and we get 10 divided by 3, and we get approximately 3.33. Again, sample size increased and our standard error decreased. The next one, we have n is equal to 16. Again, I'm just reading these values here. So we increase sample size to 16. We have standard error is equal to 10 divided by the square root of 16. We have 10 divided by 4, and we get a standard error equal to 2.5. Again, sample size increased. Let's move this little arrow here. So standard sample size increased and our standard error decreased. And we can go on and see, again, visually we're seeing that as n increases, our standard error is decreasing, and around 36, size 36, it kind of plateaus. Again, going back to that idea that a distribution of sample means will be normal when n is greater than 30. So after 30, it seems to just continue to generate this normal distribution where we have the majority of scores in the center and a few out in the tails of the distribution. So again, that's kind of an important point here, that when n is equal to 36, we start to see that there isn't a huge change in the shape of the distribution. In terms of variability, again, we're calculating the standard error. So this is a very, very important relationship. As sample size increases, the standard error of the mean decreases. So again, we're encouraged to use larger samples, because when we have a distribution of sample means with low variability, the differences that we hope to see due to treatment will be more evident. Figure 7.4, the distributions of scores versus sample means, gives us a good visual of the journey we've taken when we began with the distribution of x values, scores, and now evolved into a distribution of sample means, which allows us to engage in inferential statistics. Again, we had to begin with the distribution of scores to understand the concepts of the shape of the distribution, the variability of the distribution, the mean of the distribution, and look at how scores relate to the mean of this of a population. And then we discussed selection of a sample. So A is the original distribution where we have IQ illustrating a mean equal to 100 and a standard deviation equal to 15 points. And then we take a sample of 25 individuals, and we collect IQ scores for those 25 individuals, and we calculate a sample statistic with an average of 101.2, and we calculate a standard deviation of 11.5. Again, notice that the sample statistics, these values are different from the population parameters. Again, the difference is not due to error. The difference is explained by what we refer to as sampling error. It's just by chance that those that we selected, those 25 individuals, produced a sample mean slightly different from the population mean. But notice the similarities, that we're not deviating significantly. If those values were significantly different, let's say we selected 25 individuals who qualified for some high intelligence program, then we would see a significant difference in the sample mean. But here we're just randomly selecting individuals, 25 of them from the population, and generating these sample statistics. Next, Graph C illustrates doing this process of selecting samples where n is equal to 25 and generating all possible samples from that original population. Again, now we're talking theoretically. If we were to do this theoretically, we would produce this distribution of sample means. Now notice that the sample size is only 25. It's not that magic number of 30, but it doesn't need to be because the original distribution was normal. So the original distribution was normal, therefore the distribution of sample means, which is illustrated down here in graph C, will also be normal. Now we see that the variability is illustrated as being less in the distribution of sample means. And a question would be, why is that? Why does this graph C seem more peaked than the original distribution? The answer lies in the sample size. So we determined that we're going to take all possible samples, sample size equal to 25, and if we want to calculate the standard error of the mean given those values, the standard deviation of the original population was equal to 15. So this is our equation. So we take 15 divided by the square root of 25, and that's 15 over 5, and we get a standard error equal to 3. So the variability is now lower, but it's being expressed in standard error units instead of standard deviation units. And so again, we see that if we take all possible samples, we create this distribution of sample means that is normal. It has an average distance between a sample mean and a population mean of 3 standard error units. The mean of means, right? The mean of means is equal to mu. And again, we are working with a normal bell-shaped distribution. And at this point, we could then take a sample and see if it deviates significantly from this original population distribution that's been converted into a distribution of sample means, and see if we select a sample out in the tail over here or out in the tail over here, and then ask ourselves, is there something special about that sample, or is that sample mean simply due to chance, that we just by chance selected 25 individuals that were that demonstrated very high IQ. Now notice that those extremes do exist in the population that demonstrates a distribution of sample means. They do exist, but they exist in very low numbers. Again, this is frequency. So we see that those tails, or the values in the tails, are part of that distribution, but they're not very commonly occurring. And when I say not commonly occurring, I'm talking about probability. So the chances of obtaining those values if from a distribution or population that has not been treated. So again, it's always going to be in reference to the untreated population, the likelihood of this sample existing. Again, we do have some of those extreme values existing in the normal distribution of sample means, but they are few in numbers, meaning their probabilities are low. And again, our job is to determine if a sample mean that's generated that exists out in the tails is due to chance or due to treatment, or a difference between the quasi-independent variables. So that's what we're going to move into in the next video, this idea of how we can use these elements or characteristics of a distribution of sample means and apply what we've learned in regards to probability, the chances of something occurring.